Okay, so question number 2. A student wants to design a circuit so the battery E, which is EMF for electromotive force, which is potential, has negligible internal resistance. 2 uncharged capacitors of C1, C2, resistor R, and switch S. So the circuit can be set up so that when the switch is in one position, the battery only charge capacitor 1. When it's position discharge through capacitor 2 and resistor R. Okay, so first thing I'm going to start off, I'm going to say, look, I need my battery. Boop, boop. So I've got 2 choices, so I'm going to put a little switchy thing right here. I'd be tempted to just, do this with it and have a thing here, thing here. Now this choice is capacitor 1. Oh, that won't work because now I'm just switching which one gets the battery. That's not the way I want that set up, right? So I'm going to set it up so that, whoop. Question is the capacitor attached to capacitor? So the capacitor, this capacitor here, we want to know if it's going to be attached to this or the other. So I'm going to go ahead and put a line like this, making it clear that that is my switch. And then over here, and this is going to be a capacitor, so I got to make these equal length. Then put a second capacitor over here, and our friend the resistor right here, and then bring it on home. Okay, so they said only charge capacitor C1 when it's as the second position, because C1 will discharge through C2 and R. Okay, so again in this position, click this way. The battery powers capacitor 1, fills it up. When they throw the switch the other way, the capacitor would then, already being charged, would discharge through this cycle until these 2 voltages are what? Wait time. The voltages are the same. Okay, and the switch S is initially in position. So to charge capacitor 1, so capacitor 1 gets charged. At t equals 0, the switch is then moved to the second position. The charge as a function of time for both capacitors after the switch is moved is plotted on the graph below. Label each box with the graph that corresponds to C1, C2. Okay, well C1 starts with a maximum charge, right? It's charged, and it's going to lose its charge, so this has to be C1. And the other one's going to gain charge. Now what's interesting about this is C2 is actually higher than C1, which means it gets more charge, which means its capacitance has got to be less, smaller plates. So in order for the voltage, no, larger plates. CV equals Q. So when the voltages are the same, if one of them has a higher Q, it also has a higher capacitance, right? So these plates are much larger, so they can hold that voltage will be equal between these 2 plates, whatever they're approaching, whatever this voltage they're approaching. Okay. All right. Probably more on that later. I haven't looked at the rest of the question. Let me get the next question. All right. What circuits are as following? They give us a bunch of things to put in there. Calculate the following for a long time as the switch has been moved to the second position. Okay, so the first thing that's going to happen is the first thing is going to be charged for a very long time, correct? So, okay, so it's going to be charged. So if it's charged for a very long time, the voltage on that capacitor is going to be the full voltage of the battery. The full voltage of the battery we just discovered was 12 volts, so 12 CV equals Q. So C is for the capacitor 1 is 2 times 10 to the negative 6th, because of microfarad, times 12 equals Q, which I don't know. But I can solve for the total charge of the time, and it's going to be 2.4 times 10 to the negative 5th coulombs. Now they want to know a charge on C1 and C2, respectively. Well, we know it's going to run until the 2 voltages are equal, right? So voltage equals Q over C, so therefore when Q over C equals Q over C, we're good to go. And so Q over C, well, Q1 we don't know, over C, which is 2 times 10 to the negative 6th, has to equal 2 has to equal Q2 over 6.0 times 10 to the negative 6. Where are these charges coming from? There's no battery on the system anymore. Once you flip it the other way, there's no battery on it. Then you realize, aha, but this charge that was developed is the same charge you have at the end, right? So Q1 plus Q2 has to equal 2.4 times 10 to the negative 5th coulombs. And so there you got two equations, two unknowns. You know, I'm going to multiply both of these sides by 2 times 10 to the negative 6th. What that means, I'm going to end up with 3Q1 equals Q2, which means 4Q1 equals 2.4 times 10 to the negative 5th coulombs, which means 6 times 10 to the negative 6th coulombs is on Q1. And Q2 is whatever's left over, which is, I think, going to be 1.8 times 10 to the negative 5th coulombs. All right, checking my math. And so the next question is, what is the voltages across them? Well, the voltages have to be the same. That was our supposition to begin with, right? So I just have to pick one. Wouldn't be the bad thing to check your answers by doing this, by the way. So I'm going to say V1 equals V2, which equals 6 times 10 to the negative 6th over, what's the second one? That's 2 times 10 to the negative 6th, which gives me 3 volts. And again, I should work for the other one. 18 times 10 to the negative 6 divided by 6 times 10 to the negative 6 would also give you 3 volts. All right, let me pull up the next part. All right, so calculate the energy dissipated. It means you need energy before equals energy after, sort of thing, and the energy dissipated with the extra, right? Here's my formulas for energy on a capacitor. So here we go. 1/2. So 1/2 C. C is 2 times 10 to the negative 6 for the first capacitor. I hope I'm right on that, but it might not be. Who knows? And then its voltage was initially 12 squared, and then it becomes 1/2 2 times 10 to the negative 6 times 3 squared. This is final voltage plus energy dissipated, is what they're calling it, discharged. Energy discharged. Okay. So then it's just a matter of throwing my calculator, hit equals. So I have 1 times 10 to the negative 6. So I got 144 minus 9. So I end up with 135. 135 times 10 to the negative 6th the joules. So I would prefer to write as 1.35 times 10 to the negative 4th joules, but you know what I mean. Alrighty then. On the next piece. Oops. Okay, so what I missed. Here's what I missed. It asks not how much energy is lost in the capacitor. You have to read the question. The question is how much energy was lost through the resistor. Some of the energy ended up on the other capacitor, correct? The other capacitor would therefore have 1/2 6 times 10 to the negative 6 times 3 squared. That's going to give me another 9 times 3. So there are 27 off of that. So I'm going to get 108. This is actually 108 times 10 to the negative 6 joules. So in other words, the question wasn't how much energy you lose the capacitor. The question is how much energy is lost to the resistor, which means I have to account for the fact that some energy went in the second capacitor, right? That doesn't get burned up in the resistor. That's just still sitting there, could be used, all right? All right, let me read the next question. Right, but do not solve the differential equation that could be used to determine the time constant associated with discharge of C1. Now, nobody would find the time constant that way because you're using a differential equation. Differential equation implies Kirchhoff's law, which means we're probably going to have to do Kirchhoff's law. Calculate time constant associated with discharge of C1. Well, we're going to calculate that simply by figuring out what RC needs to be. More on that in just a moment. So how do I find the differential equation? Well, I recognize Kirchhoff's law when I hear it. So I'm going to go ahead and set up Kirchhoff's law. It says write but do not solve. That usually means you can't solve it. There's no way. So 0, make a loop. discharge. Discharge to C1. So right now we go whoop this way. So it's the battery. So if I start on one side and go through it, it's going to be uphill. So it's going to be Q over the capacitance of that, C1, minus, I'm going to lose a little IR, minus, the other battery is going to be pointing the other way, Q2, let's make Q1 and Q2, all over C2. And then in order to calculate the time, I need time in the equation, so I recognize that I happens to be the rate of loss of Q1. So Q1 over C1 minus Q1 over dt, right? R minus Q2 over C2. Honestly, not that important. Also, there's about 100 other ways you could write it, because you could write this one as whatever the charge was. We came up with the charge 2.4 times 10 to the negative fifth minus Q, and this could be Q over here. There's a couple different ways this can be written. None of them are horrifyingly important. Basically, they're asking, do you know Kirchhoff's law? And that's Kirchhoff's law right there. They'd like you to convert the current into dq dt. Now, that said, you're not going to use this to solve for the time constant. Time constant is just RC. R is, where's R? R is 1,000. C is, well, C is a little tricky because I had two capacitors on there. Now, whatever leaves one plate has to go to the other plate, so we call that in series. So we're going to go 1 over CT equals 1 over C1 plus 1 over C2. I get 1 over CT equals 1 over 2 times 10 to the negative 6th plus 1 over 6 times 10 to the negative 6th. I'm going to slap that in my calculator because I'm too lazy to do it the old-fashioned way. 1 divided by 2 exponent negative 6 plus 1 divided by 6 exponent negative 6 gives me that. 1 divided by shift answer gives me 1.5 times 10 to the negative 6th. So CT equals 1.5 times 10 to the negative 6th. So that's my constant. So my time constant would be 1,000 times 1.5 times 10 to the negative 6, which is going to be 1.5 times 10 to the 1 to negative 3 seconds. Or time constants are measured in seconds because they have to cancel out seconds when they're in the problem. And that should be, let me check math. Good. All right. So that should do it.